in this video, we're going to have a look at the control strategies for the twin rotor MIMO system. Remember that the twin rotor MIMO system is similar to a helicopter, right? Obviously, it doesn't work the same way as a real helicopter, but we have two rotors, as you can see here. We have the main rotor in here, we have the tail rotor in here, and this will be considered the two inputs to our system, because the inputs will be the voltage applied to the motors in here, to the DC motors, that will cause the movement of the blades of both rotors. The outputs will be the yaw angle in here, because this TRMS, from now on it will be the TRMS system, right? This TRMS can move this way, so side to side, side by side in here, right? So this will be the yaw angle around this Z-axis. And on the other hand, we have the other output, the second output, that will be the pitch angle, because this blade in here, this rotor will cause the movement in this way, in around this X-axis. So, as we said before, we have the TRMS MIMO model. It will be a two input and two output model. Here we have the main rotor, the tail rotor, and then the outputs will be the pitch angle and the yaw angle. As you can see here, we have named all the transfer functions that connects the two inputs and the two outputs. The naming of these transfer functions, these sub-indices in here, will be P for pitch, because the first letter is about the output, so it will be P or Y, as you can see here, because Y is for the yaw angle, and the second letter will be named after the input, M for main, as you can see here, because as you can see, this two transfer functions, they both have the same input in here, the main rotor, and here we have the T for the tail, because these two transfer functions, they both have the same input, that is the tail rotor. Then we have applied, first of all, a main rotor identification experiment, because we want to find all the coefficients for these four transfer functions, right? But we don't have the physical laws. We don't have all the parameters about these physical laws. We don't have any information about the behavior of this system. So our strategy is to apply a multi-sign signal over time here only at the main rotor. So this voltage is applied to this DC motor in here, right? And absolutely no input has been applied to the tail rotor. And we have gathered here, we have registered the outputs for the pitch angle, as you can see here on the upper figure, and then the yaw angle, the effect on the yaw angle in this bottom figure, right? So we can say that the main rotor has an effect both on the pitch angle and on the yaw angle in a different way. As you can see here, all the signals, well, they are so different. On the other hand, we have applied the same multi-sign signal over time in here, but now to the tail rotor. So we have applied to this DC motor in here, and absolutely no input signal on the main rotor, right? As you can see here, there is no effect on the pitch angle caused by the tail rotor. So only an effect to the yaw angle has been registered. So now we can say that this transfer function, so the transfer function that connects the tail with the pitch angle, is null, just because we haven't registered any effect on the pitch angle thanks to the tail rotor, the tail rotor voltage, right? So now we're gonna load all these experimental data in order to find not 4, but 3 transfer functions, PM, YM, and YT, because PT is 0, right? So first of all, we have these 2 experiments here in the current folder. Remember that we have a folder in control technology, right? So we have both signals in here, these 2 MAT files. And remember, the main experiment means that only the main rotor has been excited, right? So a voltage has been applied only to the main rotor. And here, for the tail experiment MAT file, we have registered only the effect thanks to the application of a voltage to the tail rotor, and only to the tail rotor. So we drag and drop now, for example, the main experiment, and thanks to the main experiment, we will be able to the following. Here we have the 2 transfer functions that are caused by the main rotor voltage application, right? So these 2 transfer functions will be found at first. Once we have loaded, once we have dropped this file here in the common window environment, then 4 variables appear at the workspace, right? The main voltage, the pitch angle, the tail voltage, and the yaw angle, right? So we can check that the tail, for example, if we plot this variable, the tail will be 0. Because remember, on the main experiment, that is the file that has been loaded just before, right? Here, this main experiment has no voltage applied to the tail rotor. So this variable appears at the workspace, but is 0, right? So we have the main voltage and the pitch and yaw angle effects. Well, now we're going to import this data on the system identification toolbox. You can call this graphical user interface just by typing system identification. Be careful because MATLAB is case sensitive. So this I is a capital I, and no empty space here between both words, right? So system identification and the graphical user interface appears, right? If we click on import data, then we can select time domain signals here in this pop-up menu, and we're expected to tell MATLAB that the workspace variable, first of all, will be main, because this is the input, and pitch, because now we're gonna find the transfer function that we have called GPM, this one in here. The first task will be to find this transfer function, the effect on the pitch angle caused by the main rotor. So we put here the main, the pitch, and then we can change the name of this data set. By default is my data, but you can change the name depending on your taste, right? So here by default, we let the name to be my data. Starting time, it could be 1, 0, right? It depends. The time array will start in this value. By default, I have left this one in here. And the sample time, this is very important because our sample time is 1 millisecond. So the time that spans between two neighbor samples is 1 millisecond. So the sample time must be set here in seconds. So that's why here we have a 0.001. Then the first thing to do is to pre-process this data. In order to pre-process this data, we're gonna delete the mean value about this data, but before we're expected to have two different data sets. First of all, as you can see here, by default, the whole experiment is 100 seconds in here. As you can see, the difference between the final value, the final time value in seconds is 101, and the array starts at 1, right? So we have a 100-second experiment. So we will do the following. We will pre-process this whole experiment, and we will select two different ranges. First of all, we will have an experiment from 1 to, for example, 50 seconds, and this experiment will be used in order to adjust the model, right? So to calculate the coefficients for these transfer functions, and then the remaining values of this array, so from 51, for example, till 100, will be used for the validation data. So two sets will be defined. The adjust, so that's the name. Remember, the name by default was my data. So now I have named these two different sets this way. Adjust with a time span from 1 to 50 seconds, and validation data, here you are, with a time span from 51 to 100, right? So the important thing is that now we have two different data sets from the same experiment that will be used in order to calibrate the models and then to do the validation. That is done because we are worried about the model if this model learns the data, not the dynamics. So we want to check that the model is so strong and the model has learned the dynamics of the system, not only the data, right? So that's why we validate the model with a different data set from that one that was used to adjust the coefficients. Then the important thing, to remove the means from data in the MATLAB environment, obviously. So you drag and drop this adjust data set in here, and you click on pre-process, and then in this pre-process, you are expected to choose delete remove. Well, the name is remove means, right? So then from this adjust, you will have a data set called adjust V. This means that the mean value of this adjust data set has been removed. And the same goes for the validation data. That leads us into a new data set called validation D that has the mean removed. It's important to remove the means because a transfer function is not able to explain offsets between signals, right? So that's the important thing. In order to the transfer function to learn the dynamics of the system, both signals, both input and output signals, is important not to have a mean value, right? So well, now at the end we have the original data, the adjust and validation data sets, and the same data sets but with the means removed, right? Then if you want, you can click in here, you can tick in here and at the time plot, and then a time plot will appear and you can check your data. But now let's go to an absolutely different thing, because now that we have the available data, we are going to estimate the model parameters, the coefficients of the numerator and denominator polynomials in the transfer function. So once we have here the adjust D data set, remember this is the half the experiment because it's adjust, and the, remember that it's for the mean of these signals, that the means of both signals, both input and the output, that have been removed. Well, once we have this data here in the working data, we click on the pop-up menu, Estimate, we choose Transfer Function Models, and then a new window appears, and we are expected to tell MATLAB the number of poles and the number of zeros of our transfer function, that will be GPM, right? Well, you can try different model orders, but the key is to use a good interpolating model with the minimum order as possible. Well, as a result of every model estimation, you will be given the fit to estimation data. As you can see here, we have 3 different models with 3 different combination of orders in here. Remember that the number of zeros must be equal or smaller than the number of poles, right? So here we have 3 different fit values, right? Here we have 79.31, 79.36, that is so close, and here we have clearly the winner, that is 80.58. But you are expected not only to look at this number, but the most important number in here is the FPE. That goes, this acronym goes for the final prediction error from a kit, and this number must be the smallest as possible. So in order to choose which model is the best, you will choose the smallest number for this coefficient, this final prediction error. This final prediction error puts in common, or in the same formula, the squared error, as you can see here, the mean squared error. Can you see the error that is squared in here? And 1 over n in order to calculate the mean value of the squared error. And on the other hand, we have here d, that is the number of coefficients in the model. So the higher the number of poles and zeros in the model, the higher will be number of the coefficient or the parameter d in this formula. And n is the number of elements in the data set, so the number of samples in our array, in our data array. So the key concept in here is that you can reach a smaller value, or the smallest value here in the mean squared error part, but if you reach this value thanks to a high number of coefficients in the model, this final prediction error will increase, right? So the important thing is that you reach a good interpolating model, so nearly smaller, or nearly smallest squared error as possible, right? But thanks to a minimum order as possible, right? So it's like a mixture of both concepts, right? The smallest number of coefficients and the smallest value for the mean squared error. So as you can see here, we have that the smallest value for the final prediction error is this one. So if I were expected to choose out of these 3 models, I obviously took this because it has the smallest final prediction error value. Well, now let's go to the model validation. Obviously, remember here we have the adjust dataset, but now we will check how good is the model for a new dataset. And this new dataset will be the validation 1. Remember, validation D with the means removed, right? So if you tick in here for the model output and you have this validation data in here, a new window opens, and depending on how many models you have selected here in this area, there will appear not only the original experimental data here in black, right? But also here in yellow and in different colors from black, the estimated output from the different transfer functions you have reached in the identification process, right? Well, the main difference is that this fits in here, this fits that you can see here has been obtained just only with the adjust data set, right? So it's so common to have here a smaller values for these fits because you are checking these models against a different data set, right? Because originally these fits were taken from the adjust the data set and the estimated output of the model, right? But now we have a different data set, so the fits will not be the same. Finally, once you have chosen a model, you're expected to export this model in the workspace, in the MATLAB workspace. So it's very easy. Once you double click on the model you have chosen, you can change the name of this model. By default is transfer function 1, 2, and the like. But now you can change the name of the model. It will be called GPM for obvious reasons, right? Then you click at the bottom left part of the window, you will see that there is an export push button. And once you click here, a new variable appears in the MATLAB workspace, and it is an identification transfer function object, right? Its dimension, it's 1 by 1, just because you can access the numerator, the denominator, and the like, just like a structure, a general structure in MATLAB. Well, the next step is to simulate this model. So you're expected to open the SIMULINK environment by the icon, just typing SIMULINK in lowercase letters at the command window, and then you're expected to build this model in the SIMULINK blank page, right? Here we have transfer functions, continuous transfer functions. So these transfer functions are in continuous time domain, as you can see here. They depend on S, not on Z. So here we have a transfer function, another one, and another one, because you have done all the identification process with the main experiment and with the tail experiment. As a result of the main experiment, you have these two transfer functions, GPM and GYM, because M is in common in here. And thanks to the tail rotor experiment, you have GYT, because this transfer function that connects the pitch angle and the tail rotor does not exist. In order to configure all these transfer functions is quite simple. Just because you have this structure, remember GPM here, we have this identification object, right? So it's very easy to get access to the numerator. So GPM dot numerator, GPM dot denominator, when you will be asked for them. Let's do now the coupling analysis of this multivariable system, because we have a MIMO system, we have multiple inputs, multiple outputs. Well, at the end, the system is in here, right? Because it has 2 inputs and 2 outputs. We will be expected to connect the input variable to the proper output variable in order to apply the control strategy in our system. So now, by means of the coupling analysis, we want to know which is the most interesting association between the loops. So if you apply a voltage in U1, in this input, for example, in the main rotor, which variable will be affected the most? And the other way around, if you apply a voltage in here, which variable will be affected the most, right? As you may remember, we have no connection between the pitch angle and the tail rotor voltage. So this forces us to the following conclusions. This coupling factor is the quotient between the crossed, here you are, the crossed static gains of these transfer functions in here, divided by the direct static gains of these transfer functions. Remember, the direct ones was main pitch, that's why here we have main and pitch. We have yaw and tail, so that's why here on the denominator we have the direct transfer function static gains, right? And here we have the crossed. First of all, the effect on the yaw angle by means of the main rotor, so that's this transfer function in here, right? As you can see, this is GYM, but just because GPT is equal to 0, right? Because we have no effect on the pitch angle thanks to the tail rotor voltage, it makes the coupling factor to be equal to 0. So that's why then the Bristol matrix, the relative gain array, is a perfect diagonal full of ones. It's the identity matrix, right? So that's why this tells us that the proper connection or association between variables will be the main rotor will be used to affect the pitch angle, while the tail rotor will be used in order to affect the yaw angle, because we have no choice, because the tail rotor only affects this yaw angle, right? So that's why here in the figure, we have finished this block diagram with the controllers in here, and as you can see, the pitch angle will be measured and compared to the set point, right? And then the controller will apply the manipulated variable to this input, to the main rotor, right? And here at the bottom, we have the yaw angle, this measure, that is compared with the set point for the yaw angle. And then the error will be controlled by means of this controller, and this manipulated variable will be applied to the tail rotor. That will affect only this yaw. Obviously, this will lead you to a new appearing problem that will be that every time I apply a voltage in here, not only the pitch angle, but also the yaw angle will be affected, right? So this will be considered as a disturbance, as an undesirable effect of the upper control loop. Well, first of all, in order to consider the specifications for the controlled system, let's do the simulation of this open loop model we have built before, right? We have applied a step function, a unit step function for the main rotor. Then we have done the same for the tail rotor, and the results are mixed here in the same figure, as you can see. When a unit step has been applied to the main rotor, both the yaw and the pitch, they both have been affected, right? And on the tail rotor, when a voltage is applied in here, only an effect on the yaw has been registered, right? As you can see here in the figure, the effect on the yaw angle is quite the same if you apply a voltage on the main rotor or on the tail rotor. So if you apply a voltage in here and the same voltage in here, the effect on the yaw angle, right, is more or less the same. So afterwards, this will appear in our study, right? But it's a very important thing. When you apply a voltage both on, well, on the main rotor and on the tail, you have an effect that is so similar on the yaw angle. But on the pitch, the effect is quite different, as you can see here. There is no oscillation, right? And the settling time is 1/4 the settling time for the yaw angle, right? Since both static gains, KYT, that is this in here, static gain for this transfer function, and KPN, that is this static gain in this transfer function, both are positive, when we apply the controller, remember from the previous slide, this comparison of variables will be assigned this way. The set point will be input as a positive signal, while the feedback is a negative signal, right? This is very important because this means that the error will be calculated in a reverse action of the controller, because both gains here and here are positive. So once you feedback here and then you put here a controller and do the same thing for the yaw angle, the set point enters as a positive signal and the feedback as a negative, and the same goes in here. Well, let's go now to the specifications for the control system. It's very important because for this problem, the dynamic specification for the control systems, so for the feedback systems, is to have a settling time so similar to the settling time for each angle of the open loop step response that you have here. This is the open loop step response. And as you can see, the yaw angle has a settling time of 20 seconds, and the pitch angle in the open loop step response has a settling time of 5 seconds. That's why the closed loop systems, the controlled systems, will be expected to have a similar constant time that the open loop. So that's why the desired behavior of the yaw controlled system will be a first order system with a static gain of 1, because this way there will be no error for the control system. And here, as you can see, we have the constant time for the yaw angle that will be 5 seconds. That is 1/4 of the settling time, that is 20 seconds. So we take these 20 seconds, we divide by 4 by the definition of the settling time, and we have this constant time for the specified system. And the same goes for the desired behavior of the controlled loop for the pitch angle. It's 5 seconds divided by 4 by the definition of the settling time, so it's 5/4, we have 1.25 seconds. Now we're gonna design the controller for the yaw angle. Remember that the constant time for the performance of this control system is 5 seconds in here, and this formula is what we call the direct synthesis, right? Because we have this controlled loop. We know how the controlled loop must behave, must perform, that is this, right? And we isolate the controller that because we know this transfer function from the identification procedure. We know this because depends on our specification for the controlled loop, and the only unknown variable here is a transfer function is the controller, right? So if you isolate the controller from the general formula of feedback systems, pay attention that here we have a reverse controller action, right? The isolated here formula is 1 over the open loop transfer function, so 1 over this transfer function, and then round bracket the desired behavior for the feedback control loop, 1 minus over 1 minus the desired behavior of the feedback control loop. Once you do all these calculations, we have a simple here expression for this situation when the specified transfer function is a first order transfer function. As you can see here, the formula is so simple, and then we have 1 over the transfer function for the open loop system, right? This is GYT because we are doing the yaw angle, and the yaw depends on the tail, remember, from the variable association before. And here in the denominator, we have an S multiplying this transfer function and the specified constant time or time constant for this feedback performance, right? So pay attention that here we have 1 over the open loop transfer function. So here we have the inverse of this open loop transfer function. And what's the problem? The problem is that the numerator of this open loop transfer function has a single root that is a positive real number. This will lead us to a serious problem because here we're doing the inverse of this transfer function. And when you do the inverse of this transfer function, the numerator will appear, the numerator of this open loop transfer function will appear on the denominator of the controller. And just because you have a positive real number as a single root of this numerator, that will be the denominator here in this controller, this will lead us to an unstable controller, right? So this may affect negatively to our feedback system, just leading us to an unstable control loop, right? So we're gonna do just like a trick, it's a legal trick, right? To turn this 0 into a -1. We're gonna mirror, let's figure that here we have the complex set of numbers, right? And we have a positive here. This is 1.46, and we will do the mirroring. We're gonna change this, but with a negative value in here, the same absolute value, but a negative sign in here. And this will be done just by changing this negative number into a positive 1, just like this, right? And this will be done in order to avoid an unstable behavior of this control strategy. And the same goes for the pitch angle. Remember that the formula is the same, but changing obviously the specified transfer function behavior, right? And the inverse is now about the transfer function that connects the main rotor with the pitch angle. Now the time constant is 1.25, but it happens the same. Here, by the formula, it appears the inverse of this open loop transfer function, GPM, right, as you can see here. And the numerator of the identified transfer function has also a single root being a positive number. So we change again this sign in here, and now it will appear, or it will result in a controller that will be so stable. Well, according to the MATLAB comments, the numerator for the pitch and main rotor connection, it will be, because it's the inverse, remember, so the denominator of this transfer function will be the numerator of the controller, right? That's why here, GPM denominator, the denominator of this, will be the numerator of the controller. And then the denominator of this controller will be the product of what? 1.250, because this is multiplied, remember, a polynomial in MATLAB, S1, here S0, right, power to 0. So that's why here we have the constant time in here, right, that multiplies by S. That's why 1.25 in here and a 0, because there is no independent term in this polynomial. And it's the product with the numerator of this transfer function. But remember, this numerator needs a sign change in here. And the same goes for the yaw angle, a sign change in here. So that's why here I do the absolute value of this array, because the absolute value, this is positive. So this will be positive again, and this negative, because it's the absolute value of this coefficient, it will be also a positive, right? It's like a tricky thing, just to change this numerator into its absolute values. The same goes for the controller of the yaw angle and the tail rotor. And finally, we built in our SIMULINK environment, remember, here we have the model, and then we apply the controller in here and the controller here at the bottom. Remember that here we have the numerator for the controller pitch main, denominator, and the same goes for the yaw and tail rotor. A very important thing here, we have a limiter block between 0 voltage and 10 volts, because this will be the maximum value for the real system, right? And this will be the minimum value. So no negative values for this manipulated variable. And the same goes for this, right? Here we have also a limiter. Remember, the controller here, it's configured as a plus minus, remember? So we have not a direct action of the controller, we have a reverse action of the controller, right? So these are the simulation results. Here at time t equals to 0, we have a set point for the pitch angle, and you can see that the pitch angle is perfectly controlled thanks to the main rotor, right? But remember, the main rotor has also an effect on the yaw angle. So that's why here it appears something that it's so weird, because it's the undesired effect to the yaw angle caused by the main rotor, because the main rotor has an action in order to get the pitch angle equals to 1, that is the set point, right? But just because it affects also the yaw angle set point is 0 until t equals to 30 seconds. That here, the set point for the yaw angle changes to 1, the same as the pitch control. But as you can see here, the yaw angle is affected by the main rotor, is an undesirable effect. Obviously, it's controlled. At the end, the effect is 0. But can you see here the huge value here of the disturbance? Well, at the end, the yaw angle is controlled thanks to the tail rotor, and as you can see here, there is no overshoot, and it seems that the performance is fine. But let's check about the time constants for both systems. Remember, the pitch angle, the settling time, well, the time constant was 1.25. So a settling time of 5 seconds. And as you can see here, 5 seconds is in here, and obviously the system reaches the set point at 5 seconds. So it's fine. Here we have a settling time, remember, of 20 seconds, a time constant of 5 seconds for the yaw angle, remember? So we have a 30 in here, so 50 is 20 seconds long, 20 seconds far. So here you can see that the settling time is 20 seconds just because the set point is reached by the process variable, by the yaw angle, 20 seconds later, right? So the performance is fine. But as you can see here, there is an undesired effect to the yaw angle caused by this main rotor action. These are the experimental results because these were the simulation results. Now we have the experimental results. Remember the set point for the pitch angle at t equals to 0. Here we are. It's a 5 seconds. Remember, here we have 10 seconds, so 5 seconds. There is a small oscillation in here, but, well, we can accept this, right? It's 5 seconds for the settling time. And here we have the yaw control. It's fine, but it appears the undesired effect to the yaw angle again. As you can see here, we have this undesired effect. How can we fight against that? Well, by means of the decoupling. The decoupling is based on the feed-forward control. Remember, the feed-forward control consists on the following. We have a disturbance for the output of our control system, right? And we can measure this disturbance, and we know also how this disturbance affects our system. And remember that this feed-forward controller affects the system with the following criteria. Here, a disturbance appears, and the effect by this way will be cancelled by the effect of this other way, right? So the feed-forward controller transfer function will be calculated according to these two elements. At the end, the controller, the feed-forward controller, will be minus the disturbance divided by the transfer function here for the open loop, right? But if we translate these elements into our problem, remember, our problem is the effect of the main rotor on the yaw angle, right? So this will be the transfer function of our disturbance. So we know perfectly this transfer function because we have found all the coefficients in our identification process, right? This is the transfer function that is used when you control the yaw angle by means of the tail rotor. So the controller for the yaw angle, so the decoupler of the yaw angle from the main rotor will be calculated as follows. This controller will be a static one, right? So that's why here it's a K, not a G. It will be not a dynamic controller. It will be a static controller for our purpose, right? So this controller is calculated as minus the gain of the disturbance here, so the static gain of this transfer function divided by the static gain of this transfer function. This way, the static effect of the disturbance through this way and through this way will be cancelled. So how can we translate this into our simulation model? Well, we put a gain in here. The input of this gain block comes from the main rotor, right? This is the controller action. And then here, this output is added to the feedback controller for the yaw angle. And how this gain is configured? Minus K sub Ym, that is the gain of the disturbance, divided by Kyt, that is the static gain of the proper transfer function. As you can see here on the simulation results, the effect has been diminished, right? So the undesired effect is now smaller than before. Remember that before it was so huge, now it's smaller. And when you apply this on the experimental aircraft, well, it's not really an aircraft, but you know, it's the TRMS, here the undesired effect is clearly decimated.